Hey guys, welcome to the channel Eric's tutorial. I'm Eric, and this is our first video. I don't know how this channel going to be. Hopefully, I will get a few subscribers. And I'm sorry if there's any random noises because I do the recordings in my dormitory. Anyways, now today we are talking about Thevenin's theorem and Norton's theorem. I think it would be useful if you are studying electrical engineering, or if you're the same as me, studying mechanical engineering or any other discipline that needs to use electricity. So these two theorems, why I put it together in this video, because they are all talking about power sources. So for power sources, we have these two kinds. One of them is voltage source, and one of them is current source. So voltage source is most of the time like this, and current source you will probably see it in the circuit like this. So yeah, just for example. Now Thevenin is Thevenin's theorem is for the first case, and the Norton theorem is for the second case. Yeah, you will get it soon. So to explain both of them, we use this circuit as an example. This is a voltage source, an ideal voltage source with 25 volts. This is 5 ohm resistor, and this is a 4 ohm resistor. This is point A, we're gonna use it later. This is an 8 ohm resistor, this is point B. And here we also have a current source, 3 ampere. Here we have the last one, 20 ohm. Now, if you have some basic knowledge for electricity or circuits, you will probably know what is this word. Load. So it's just yeah, I won't go through it. So load. Now in this circuit, we treat the resistor between point A and point B as the load, which is this one, the 8 ohm resistor. This one is the load. Now, since this one's the load, then of course the rest of the circuit, that is all of these between point A and point B, these are the stuff we want to deal with, or Thevenin and Norton want to deal with. So what are we doing is we want to convert all the stuff except the load into another voltage source with VTH. TH stands for Thevenin, and RTH. This is still point A, this is still point B. Do you get it? We want to convert all the stuff except the load into another Thevenin voltage source. Now, what are we going to do is actually two things to calculate RTH and VTH. How do we do that? No worries, Thevenin has already explained it. Step 1, you have to determine which is the load. We have also I mean, yeah, we know that the 8 ohm is the load, so we remove it. That's pretty natural. Okay, and then let me erase it. So after we remove this 8 ohm, we have a circuit like this. Now what we can do is we put a voltmeter here. Connect your black pen and red pen to these 2 points, A and B. Okay, and then you will get VTH. The reading on the voltmeter is actually VTH, but unfortunately, if you are in an exam, the circuit would be on paper and you don't have any voltmeter as well. Okay, so how do we calculate it on paper using pen? I believe you've heard about node voltage method. Okay, or mesh current method. Okay, these are the, I believe some guys already get it. Yeah, right after they see these 2 words. Yeah, because it's just a simple circuit. Okay, and you got an open circuit between AB points. You just calculate the voltage between point A and point B, which is the same as the voltage between these 2 points, right? Because it's open circuit. Okay, if you don't know about node voltage or mesh current, I will talk about it in another video. Anyways, so yeah, all good. We have the VTH ready, and the last step is to calculate RTH. How to do that? For RTH, what Thevenin say is that we have to first cancel out all the sources, all the power sources, no matter it's voltage source like this one, 25 volts, or current source like this one. How do we cancel their effect in this circuit? How do we cancel it? So if you want to cancel it, first we have to know what are their effects to the circuit, so that we can cancel it, right? So for an ideal voltage source, of course, the major effect is to provide 25 volts. Okay, so to cancel it, we just erase it. We don't want we don't want this part to contribute any voltage. So no 25 volts, nothing. And then, beside that, you should notice, this is important, because apart from providing 25 volts, when you're analyzing a circuit, an ideal voltage source also acts like a resistor with infinite large resistance. So, to cancel that out, we turn the voltage source into a cable whose resistance is 0. That makes sense. So next, we do the same thing to the current source here. First of all, we don't want it to provide any current anymore, so no current. Second of all, an ideal current source acts like a resistor with 0 resistance. So to cancel that out, we turn it into a resistor with infinite large of resistance, which is basically open circuit. And that's it. So what I've done is turn all the voltage source into a cable. In other words, short circuit all the voltage source and open circuit all the current source. Why did we do that? It actually makes sense because we want to calculate the RTH here, which is the equivalent resistance between point A and point B. Of course, we only want resistance. We don't want any other thing to have any other effect, such as current source or voltage source. So we cancel out all the effects from these two things in the original circuit. And after we've done that, between A and B is the RTH, which is pretty, yeah, it's apparently 5 ohm in parallel with 20 ohm and plus another 4 ohm. You can get that really quickly, I believe. So yeah, that's it. That is the Thevenin's theorem. Two things: calculate VTH, calculate RTH. Now, the Norton's theorem is to turn the original circuit into a Norton current source or an equivalent current source. This is point A, this is point B. Now, surprisingly, or not surprisingly, this resistor is still RTH, and the calculation method is also the same, just the resistance between point A and point B. And yeah, so you get it. Now, the difference is this RTH in the Norton theorem is placed differently with the RTH in Thevenin theorem, because you'll see point A, point B, point A, point B. This one is in parallel with the IS, and this one is in series with VTH. Okay, sorry, this one should not be IS because we want to emphasize this one is the Norton's circuit. So IN, okay? N for Norton, TH for Thevenin. Now you can also call this one RN, but the value is the same as RTH. So yeah, now all you have to do is to calculate IN. How do you do that? It's pretty much same, but a little difference. So we recover the original circuit. This is the V, right? The source was 25 voltage, and this was 3 ampere. Okay, it's pretty much the same. It is the current flowing between A and B. So in other words, you have to first short circuit A and B, and then you calculate the current. How do you do that? As I mentioned, mesh current method or node voltage method. Yeah, and that's all. You get IN. Two things after the main topic. First of all, somebody may ask a question like this. In the Thevenin's theorem, you probably noticed that we open circuited A and B, and we want to measure the voltage across A and B. Okay, So as I mentioned, the voltage between these 2 points are exactly the same as the voltage between these 2 points. So somehow it seems that we ignored the effect of the 4 ohm, because no matter what it is 4 ohm or 4,000 ohm, it won't affect the voltage between these 2 points. Thus, won't be affecting the voltage here, won't affect the voltage of VTH, but it does matter because we've considered it in the RTH, right? The RTH is 5 parallel with 20 plus 4. So if you change the 4 into 4,000, you actually change this 4 into 4,000. So you actually modified the equivalent power source. So yeah, maybe that's a dumb question, I don't know.